Welcome to our second Kavli lecture of the academic year. And it's a great pleasure today to introduce our lecturer, Professor Risa Wechsler from Stanford University. I think you're the Humanities and Science professor. Presumably that doesn't mean you have to teach sociology and things. But so in Stanford, Risa is the director of our sister Kavli Institute, the Kavli Institute for Particle Astrophysics and Cosmology. And she's also a director, the director of a new Centre for Decoding the Universe at Stanford. That sounds very exciting. So Risa's research tackles some of the real big questions in cosmology and astrophysics. How do galaxies form and evolve, the nature of dark energy, of dark matter, and the formation of the Milky Way. And she does this combining computational, observational, and sort of data science techniques. She's played a leading role in many major surveys. These include the Dark Energy Spectroscopic Instrument, and Risa was the co-spokesperson from 2014 to 18 for that instrument. And now she serves on the Rubin Observatory's executive board for the Legacy Survey of Space and Time. So Risa's scientific and her leadership contributions have been recognized with many awards and honors. Perhaps just mention the most recent ones. So in 2023, she was elected a Fellow of the American Academy of Sciences. And it was fantastic news that this year you were elected a member of the National Academy of Sciences. So many congratulations, Risa. So we're delighted to welcome you to Cambridge. Thanks so much for taking the time to come and visit us. And we're really looking forward to your lecture, which is entitled Unveiling the Nature of Dark Matter with Small-Scale Cosmic Structure. Thanks very much, Risa.
Thank you. It's great to be here. Already had fantastic conversations with so many of you, including many graduate students. So really already enjoying my time here. And it was a pleasure to be back so quickly after last year's 50th anniversary celebration. As was mentioned, I work on many things across the universe, but I've recently been close to home for a cosmologist, thinking a lot about how we use sort of the smallest cosmic structures that we can measure to learn about the nature of dark matter. And I think this is a really exciting area, both theoretically, computationally, and observationally right now. Let's see. Okay, there we go. So I think the next decade is going to be really exciting. Many things are either have just started taking data or about to start taking data or will launch soon. And if I forgot your favorite survey, it's only because there wasn't enough room on the slide. It really is going to be a tremendous decade in astronomy because of the richness of the data that we have coming at us. Imaging, spectroscopy, multi-wavelength data, multi-messenger data. So it's just really exciting and a whole new dimension in the time domain that is going to be opened up in the near future. And just a small, tiny piece of this is like thinking about the numbers, kind of roughly where we were, at some time when survey astronomy started to kind of where we are now to what's coming at us. The number of spectra that we have, the richness of the imaging that we have, and then many details of the actual objects that we can discover are just really, we have a lot coming at us, and we have to think hard about what we do with all of these data. So many of the missions that are on my last slide are really driven by sort of precision cosmology. So they're going to test the standard cosmological model at, just incredible precision. These are just some examples of, kind of 1% precision on the Hubble parameter from many independent methods, fraction of a percent measurement of the expansion history over, most of cosmic history. Similarly with the growth of structure, we'll try to measure inflation much better and get precision constraints on neutrino physics. But many of these surveys, even though they weren't necessarily designed for this purpose, will tell us a lot about the real microphysics of dark matter. And this is, of course, an important question because we don't know what dark matter is. Our ignorance is very large, right? So about 90 orders of magnitude in mass is our current ignorance of, what is the mass of the dark matter particle. And so I'm not going to talk about every way there is to probe the dark matter, but I'm going to focus specifically on how do the smallest observable scales of structure formation tell us about the physics of dark matter. And in particular, can we detect any deviations from cold dark matter? Is there less or more substructure, different internal structure of dark matter halos, or any other sign in our astronomical observations of interactions, either between dark matter and itself or between dark matter and standard model particles? And specifically, what I'm going to focus on today is, can we actually get to that regime which is at and then hopefully below the regime in which galaxies form? And ideally actually measure what is the minimum mass at which galaxy formation really happens, and then go further and detect the dark halos that are below that limit. So, one way to think about what we know about dark matter is just thinking about the power spectrum. So these are measurements of the power spectrum from many different sources, including the CMB and large surveys. And you can see that, at least at the time that this plot was made, those measurements sort of stop, at, if we think in terms of halo mass, it's things maybe a little bit smaller than the Milky Way. And, a pure cold dark matter is like just an extrapolation of this simple line. And in that context, what that means for structure formation, it means that the dark matter particle, the free streaming length of the particle is small enough that it doesn't impact structure formation on really any measurable scale. And that interactions, again, either between dark matter and itself or between dark matter and protons or electrons, don't impact structure formation. Now, this model makes a whole bunch of predictions, and that includes the number, clustering of dark matter halos, how they cluster, how they merge, what their internal structure looks like, how much substructure they look like. And, to some extent, we've had a lot of these predictions, for more than 20 years. You see that some of the plots I chose here, were done right around the time we started to be able to resolve substructure in numerical simulations. And so, we know how to make these predictions in the absence of baryons and in this simple dark matter model. And this model is really well tested on large scales. So we know that whatever the universe is doing, it has to look like this on large scales. But we really don't know what it's doing on scales below the scale that we've tested it. And there are, given that we don't know what dark matter is, we haven't found the WIMP yet, and there really are many plausible models of dark matter that do different things on scales that we haven't measured yet that look identical to CDM on large scales. So those include warm dark matter. It includes dark matter that's very light, like an ultralight axion. It includes self-interacting dark matter that has interactions with baryons, dark matter that decays late. I've spent some time thinking over the last few days about some new kind of axion models that have different kinds of impacts on the power spectrum. So there's lots of different ways that dark matter can impact. And two of the ways that it impacts it can impact basically how clumpy the dark matter is, and it can impact the internal structure of those dark matter clumps. So that internal structure, in addition to the number of dark matter halos, the internal structure is sensitive to things that are different from CDM. This is an example from a simulation by Mark Vogelsberger, who shows that, in CDM, the profiles can sometimes be chord. It's actually more complex than that, depending on the model. Sometimes they can be chord, sometimes they can actually have core collapse. So they actually, SIDM in general predicts like a wider diversity of profiles. But this has been, as someone who has paid attention to this field for a few decades, very fraught, largely because a lot of the comparisons that have been made so far have been made in a regime where feedback is really dominant, where the main thing impacting dark matter profiles is supernova feedback or other things that can actually do interesting things to dark matter halos. But it does look like now with modern simulations that if you push to the left of that plot, really into the regime where you have very few stars, then that is a good place where it's much less sensitive to feedback. That's also good to go to small scales because you just then have a longer lever arm with probes of the dark matter models compared to groups and clusters. So there's many interesting models of self-interaction where there's a velocity dependence, and so actually having the widest mass range that you can possibly probe is interesting. Okay, so coming back to this plot, basic point here. So here's a whole bunch of other models that do different things to the power spectrum. You can see a lot of the models suppress the power spectrum, but there actually are models that give you more power for various reasons. And so ideally, we actually want to look for both of those effects. And so the thing I'm going to address in this talk is, can we make good measurements in this regime, kind of below the limit where these points are, and a few orders of magnitude below that. So there's lots of different ways we can think about small-scale structure, ways we might be able to probe it astrophysically. It includes looking at the smallest galaxies in the universe, includes looking at strong gravitational lensing, also stellar streams in our own galaxy and actually also in nearby galaxies that can be perturbed by small structures, whether they have galaxies in them or not. There are other probes. Lyman Alpha Forest is a very interesting probe that I've talked with some of you already about today. High redshift galaxies, 21 centimeter, I think has quite a bit of promise for the future, but is not yet providing any constraints. This is a nice plot from a recent paper that sort of shows, the range of K scales and redshift scales that different kinds of probes can constrain dark matter physics, all the way from the CMB anisotropy down to these smallest scales. But I'm going to focus kind of on this regime, and specifically, I'll talk about these three probes and the complementarity between them in this talk. So I think dwarf galaxies currently provide the strongest, or at least competitive with other probes, the strongest constraint on small-scale power. And it's actually a very simple calculation. It's basically the fact that if you have a lot of low-mass galaxies, you rule out dark matter models that don't predict a lot of low-mass clumps. It's a very, very simple argument. And I think these measurements will improve quite a bit in the near future and also have potential to constrain self-interacting dark matter once we can actually well measure the velocity dispersion of very small things. These other two probes, I think, are very, very interesting. Neither of them is quite there yet in terms of being at the level of data analysis or theoretical modeling that we need it to be, but I think they're both very, very exciting. And I think they both have near-term potential to probe smaller scales than dwarf galaxies can possibly probe, because both of them don't depend on having a galaxy in the clump that you're looking for. Okay, so I'm going to just first talk to you about some work that we did a few years ago, looking at the dark matter constraints from dwarf galaxies in the Milky Way. And I just always love this picture from Gaia, because you can actually see the large and small Magellanic Clouds. But of course, in the last few years, we've detected a whole bunch more satellites that orbit the Milky Way. We have something like 60 galaxies that are now confirmed in the Milky Way. Actually, this plot is out of date. Some of those empty circles should be filled, because we've confirmed several more of those. Why is this interesting, right? If we find a whole bunch of these, we can then ask whether the clumps that we predict in our dark matter model are consistent with the small things that we see. So again, warm dark matter and many other models that behave like warm dark matter suppress the number of dwarf galaxies. So the orange lines on this plot are examples of what warm dark matter can do to the power spectrum. So this is the suppression of the number of galaxies you would see as a function of the halo mass. And you can see that, Warm dark matter of about 5 keV has a pretty big suppression at about 10 to the 8. If you get up to 17 keV, it's quite small. And this is partially degenerate with which halos form galaxies and what galaxies they form, but it's not perfectly degenerate, so we actually can distinguish those things. So, of course, one of the things we want to do is make very robust predictions. Different models in detail make different predictions for what that substructure looks like. This is an example from recent work by Ethan Nadler that does a really nice simulation suite of warm dark matter, fuzzy dark matter, and dark matter that has proton dark matter interactions. And the phenomenology is to 0th order sort of self-similar with, is very similar to warm dark matter, but in detail can actually be different for different dark matter models. You can have impacts on the number of dark matter halos, but also their anisotropy, the radial profiles of substructure within your halos, and the internal density profiles of the substructures themselves. So those are all things that, in detail, one wants to actually, really simulate for the models of interest. But it's still true that to sort of first order, these models can have sort of similar impacts on the transfer function or the power spectrum, and then consequently have similar impacts on the subhalo mass function. And so what you see here is a set of 3 models: warm dark matter, interacting dark matter, and fuzzy dark matter, which suppress the power and then impact the number of halos you have. This is as a function of mass. And 1 here is lambda CDM. And so what we did a few years ago was we took about 3/4 of the sky, which had measurements from the Dark Energy Survey and pan-stars, about 40 galaxies detected in that part of the sky, these Milky Way satellites. And we asked, if you have a very flexible model for putting your galaxies in dark matter halos, really maximally flexible, and you assume this subhalo mass function, what do you get for the luminosity function? Okay, and the bottom line of that is that current satellite observations are sensitive to about a 25% suppression in the subhalo abundance relative to CDM. And that's at about a minimum, at a halo mass of a few times 10 to the 8. So that means whatever you do to the power in a model that suppresses power, you can't suppress more than about 25% at that few times 10 to the 8. And that is really just from the existence of these 60 galaxies. They need a halo. I'm making an assumption that these galaxies need a halo to form in. But as long as you make that basic assumption, you get really nice limits on these models. So warm dark matter, you get a limit of that it has to be greater than 6.5 keV. That's basically saying that the dark matter, if it moves, basically you have a constraint on the free streaming length that it can't be larger than the minimum halo that you have. Similarly, for interacting dark matter, you have those interactions sort of similarly suppress those numbers. And for fuzzy dark matter, you can think of this that like the wavelength of the dark matter is constrained, that it has to be smaller than the size of these galaxies. So that's the basic idea. But this is not the sum total of the models you can constrain with these data. And I actually think that's what's quite exciting about these small-scale structure probes. We can do a lot of this in ways that is quite generic to the models that we're constraining. Not all of it, because as I said, there is interesting phenomenology in the density profiles and the details of the anisotropy. But after we published this, we were able to put constraints on a bunch of other models that are also interesting. And so whenever your favorite particle theorist comes up with a new model, you can say, okay, well, does it produce structure on these scales? Okay, but I'm mostly going to talk in the rest of the talk about the future. So what are the ways in which we can improve these constraints? And what pieces do we need to put together to push this as far as we can go? So, of course, there are ways to improve the modeling, or to add complementary data to reduce degeneracies. We were actually quite conservative in that analysis, so there's a lot of ways you can put constraints on that. One key uncertainty that's been with us for a long time is the mass of the Milky Way, and that I think has potential to be better measured. We expect that there's a whole bunch more Milky Way satellites to be found, and so finding more will do better than this. In the analysis I just told you about, I did not actually use detailed information about the velocity dispersions or the masses of the satellites, and so when you add that information, you get stronger constraints. The reason we didn't add it initially is because it is actually quite a bit harder to model, so you have to be quite careful about that, and that's something we're working on now. We can also find satellites in external systems, and even though you can't go as deep as you can in the Milky Way, it actually turns out that it really appears that the substructure function and the luminosity function is relatively set by the massive end, sort of due to the formation history of the dark matter halo. So if you can really understand where the Milky Way sits in the full distribution, that also helps you somewhat. But then what I'm going to talk about mostly here is, how do we push this, but then also how do we look for more sensitive methods, including lensing and streams. So I'm going to spend a little bit of time talking about the data that we either are just starting to get or is coming soon. As I said, I think it's a very exciting time. We have spectroscopic and imaging surveys that are now actually mapping most of the sky. And we also have other things that can't quite map quite as much volume, but can do so at much higher resolution. So I'm going to talk about DESI, Rubin Observatory, Roman, and VIA. So let's just spend a few minutes on DESI. So DESI was really motivated as a cosmology survey to match as much volume as we possibly can. DESI is doing a phenomenal job at actually mapping a very large volume in the universe to really try to get high precision measurements of the dark energy equation of state through the expansion history and the growth of structure. But it turns out the same survey is also very good at finding small galaxies, nearby galaxies, and mapping the Milky Way. And so with bright time, DESI has surveyed actually already about 10 million galaxies in the Bright Galaxy Survey, which is, although it says bright, it's a sort of magnitude limited survey that's about 2 magnitudes deeper than Sloan. So it's a quite powerful survey. We have an ancillary program in DESI that's enabled us to push about 1.5 magnitudes fainter to get dwarf galaxies in the nearby universe. And then we already have a spectra of about 10 million stars in the Milky Way survey. DESI is a 5-year survey, but it looks like very likely we'll have a 2.5-year extension through 2028, and most likely a second stage for another 5 years after that. So I think we actually have quite a bit to go in terms of just continuing to use this instrument to map as much as we can, both nearby and out to very high redshift. For those cosmologists in the audience, DESI 2 is going to be primarily targeting Lyman bright galaxies and Lyman alpha emitters, and to get more volume. Just a few things from the Milky Way working group. Although DESI, this is not part of what DESI is supposed to be doing, sometimes you get lucky and you can use DESI to do other things. And it's really good at doing other things. So this is an example. Ursa Minor is a relatively sort of on the low end of the classical dwarf regime. And this is an object that it's pretty big for a dwarf galaxy. So it took more than 10 KICC hours to get close to 900 members with this thing. And in 60 minutes on DESI, we got more members than that and much further out. So you could imagine what you could do with these classical dwarfs if you're able to just spend a tiny bit of time on these things. Similarly with GD1, this is actually just the beginning of a GD1 program with DESI, where it was just sort of some random fibers mostly, but we've got a larger program happening here. And so I'm optimistic that we'll be able to do more targeted Milky Way observations in an extended DESI mission and get really great measurements of those dwarf galaxy profiles. So you can find substructure in the Milky Way with DESI. This is an example of a substructure, basically a stream that we found in the spectroscopic data. It turns out it actually was found before in Sloan, but then kind of very barely found and then never looked at again. So not studied in any detail. It turns out you can study it really well with DESI. And I'm most excited about this technique to basically be able to push the low surface brightness regime of dwarf galaxies, where you actually might be able to detect these sort of, sometimes they're called stealth galaxies. They're too fuzzy on the sky to easily find in the photometry. You can actually find them maybe better in the spectroscopy. I've been having a lot of fun with a dwarf galaxy survey, which comes both from the Bright Galaxy Survey, the faint end of the Bright Galaxy Survey, but also from this secondary target program that I mentioned. And we have a paper coming soon that's got 350,000 spectra of galaxies less than 10 to the 9. So I don't know. For me, I've been thinking about these faint galaxies for a long time. This is a truly stunning number. When I started working on these tiny galaxies about 15 years ago with a Saga survey that we started, there were about 10 galaxies in the local universe that had spectra. So this is really, really exciting. We're already able to use DES data to measure the lensing profiles of these galaxies for halos that are maybe for galaxies that are a little bit bigger than 10 to the 9 in solar mass. In stellar mass. And with LSST, we expect to be able to measure those lensing profiles, maybe 2 orders of magnitude fainter. And this is just a fun thing that my graduate student Viraj found in the spectra. There's a bunch of supernovae you can find in the spectra. It's just really cool. That's just a fun tidbit. Okay, coming next, very, very soon, Vera Rubin Observatory's Legacy Survey of Space and Time. So this is a 3.2 gigapixel camera that we built at SLAC. It goes on this very large telescope that has this really nice 3-mirror design, and it's a telescope that allows you to go very fast. And so you can simultaneously, so that camera has a field of view that's about 45 times the size of the moon. So every 60 seconds, you take that 3-degree picture, and then you do it again about 1,000 times a night, and then you do it again for another 10 years. And so we're going to have about 20 terabytes of data a night. We'll survey every part of the sky about 800 times. And every night we expect to see about 1 million things that are different than the last time we looked at them. So we will simultaneously get a very deep image and an incredible movie of everything that is happening on so many scales. So this has been a very long journey. I think when I was hired at Stanford in 2006, it was because LSST was just going to be the next thing that we did right away. Anyways, the camera is on the telescope, and this is what happened when they turned it on. This was just 2 months ago. And the really exciting thing is that on Monday, your face can look just like these happy faces. The first images from Rubin will be public on Monday at 8 o'clock in the morning, California time, which is why I am not staying longer. But I think you will all be here seeing them yourselves. So it's just really, really, really exciting. And I think the most exciting thing about what Rubin is that it really is kind of, a beautiful map that we can do anything with. And so, I really think it won't be the only important instrument at all, but I think it's going to be a piece of many things that we discover in astronomy. As I said, every night we expect about 1 million things to be different than the last time we looked at them, all the way from the solar system to all of the moving and changing stars, all the way to supernova, 11 billion light years away, gravitational wave counterparts, all kinds of exciting things. I hope, we really will be probing a new regime in the time domain that hasn't been possible before, so I expect us to have some surprises. And I hope the most exciting thing from Rubin is something that's, that I haven't thought of. For the purposes of my talk, there's 3 things that I want to highlight. The first is we will have beautiful, beautiful lensing maps, and those will be fantastic for cosmology, mapping how the dark matter over half the sky evolves, over 10 billion years. So that's great for dark matter and dark energy. But it also is great for actually measuring the mass profiles of very small galaxies. And I think we have now techniques that will allow us to push that into a really interesting regime. We're expecting to map about 20 billion stars in the Milky Way. And so there's a lot you can do with that. I think probably many things you can do with that are not going to be listed here. So we definitely will find new dwarf galaxies, and we will find everything that happened to the dwarf galaxies and their globular clusters as they came into the Milky Way and got destroyed. We also expect to find a lot of strong lenses, which are very interesting for a number of reasons. They can provide dark energy constraints, but they can also help us find the smallest galaxies and dark halos. So for the Milky Way, LSST can actually detect main sequence turn-off stars at the edge of the Milky Way. So that's really a new regime. It's about 1,000 times the volume of what was possible, with DES, for example. And so we expect to find, I would say at least 50, maybe 100 new satellites in the Milky Way. Most of the satellites in the southern footprint, LSST actually will be limited in this regime by its star-galaxy separation. So this is that actually will be the fundamental limit, and so this is a reason why you would love to have Roman data over as much of the footprint as you can, for example. We also expect to find new stellar streams, hopefully at larger distances, which is really interesting because you want to really study the dynamics of the Milky Way over as much of its radius as you possibly can. Okay, so I want to get to the key point of the talk here, which is that CDM makes a very clear, straightforward prediction that galaxies form in dark matter halos, but they only form in dark matter halos above a certain size. And we don't know exactly what that size is, but we have a pretty good idea. And it's probably not too much smaller than 10 to the 7 in terms of the halo mass today. If you have only H1 cooling, then you're at sort of 10 to the 8, and our current limits are actually below that. So whatever this limit is, it can't be too far below where we are already probing. So I think really want to know what is this limit. That tells us something fundamental about early galaxy formation, and then hopefully detect dark halos below it. So if we detect dark halos below this limit, I actually think that is a really big deal because it's a really essential prediction of CDM, and it tells you that dark matter has to exist in those clumps, independent of galaxies. It also tells you that, for the purposes of galaxy formation, if dark matter is not cold, it doesn't matter too much. So that's also interesting. And if you convince yourself that you have an experiment that is sensitive enough to detect these things and you don't detect them, then you rule out CDM. So that's it basically says that dark matter looks just like CDM on large scales, but it's not truly cold. That model breaks down at some point. So both of those things would be very interesting. Okay, so how do we actually do this? Well, in principle, I think there's at least 2 ways, and probably more, but I'm just going to talk about these 2 ways to detect dark systems. Neither of these ways depend on there being a galaxy. They're just dependent on there being a clump of stuff. So in the strong gravitational lensing case, you're looking for substructures in the lens that distort the image. And in the stellar stream case, you're looking for the impact of dark halos on the streams themselves. Okay, so gravitational lensing, right? So basic idea, you've got a high redshift background source, and then you've got a massive halo, which is the lens, and that massive halo has a bunch of substructure in it, presumably, and then you see some feature like this observed image. So in practice, these kind of images are sensitive to how much substructure you have in your lens, and also sensitive to substructure along the line of sight. And so this is a simple model here where, where the number is just a function of a normalization that tells you about the amount of substructure. But you can see that that actually impacts the lens image. It's actually a little bit hard to see in the image on the left, but if you look at, you can actually look at the subhalo convergence map and then look at the residuals, and you can clearly see that those things are different from each other when you change the amount of substructure. This is a really hard measurement, and there are multiple ways to do this with different kinds of data sets, different kinds of modeling. I would say so far it's been a very hard game. So what do I think is needed? I think it's really hard, but I actually think it's within reach in the quite near future. So I'm going to talk about one technique, but there are others. So first thing you need is you need a lot of lenses with great images. That is something we actually already have and is going to get better fast. I'm not sure that our modeling will keep up with the quality of the data. So we already have, let's say maybe 100 lenses, maybe 30 that are easy to use for various reasons from Hubble. But actually in the relatively near future, if all goes well, Roman should launch in not much more than a year. And Roman has about 100 times the field of view of Hubble and about 1,000 times the survey speed of Hubble. So this is what the footprint looks like from Roman. And you should expect one strong lens or more in essentially every Roman pointing. So we will find a lot of lenses. I recently co-chaired this committee that made recommendations for the High Latitude Wide Area Survey. That's one of 4 parts of what Roman will do. It will also do time domain. It will also survey the galactic bulge. And then about 25% of the time on Roman will be open to the community. But this is a really new mode for space-based telescopes that mostly Roman is actually going to be a survey instrument. So I think it's actually really a really exciting new regime. Okay, so lots of lenses. You have to think really hard about the inference. There's lots of ways to confuse yourself and to be biased in these lenses. Strong lens modeling is notoriously a bespoke by hand, massage your lens like it's perfect, and then you get an answer at the end of a very long process. So that's not going to work for this number of lenses. So we've been really thinking hard about how to do this inference in a fast way and in an unbiased way when you have lots of confounding factors. And I think we're getting there. This is a result that shows we can get unbiased results for 100 lenses with this analysis. But it actually also really has to be fast. That's another thing that can be quite challenging. And so we've been able to speed this up by a few orders of magnitude recently, and that's really great. This is a really nice example of simulation-based inference where we've actually made the simulation step as fast as the inference step, so it's no longer the limiting factor. So that's really exciting. Another thing that's actually been very challenging with strong lensing in general is that actually there are a lot of degeneracies between the source and the amount of substructure. So if the source, we've recently learned from JWST, for example, that high redshift galaxies are very messy, clumpy things. They're not smooth. That actually can confound your substructure results. So you really need to think hard about making sure you have a representative sample that has all of the complexity of your source system. So really nice paper coming soon from Sydney Erickson and Sebastian Wagner-Carrena that has a sample that's about 80 times larger than we were using before. That actually was the limiting factor for what we had. And then the last thing that I think you need is really much better predictions from dark matter models than we have now. I'm going to spend a little bit of time on that at the end of the talk. So that includes, really what is substructure doing even in the inner regions of the systems where, tidal stripping is really important. What is the detailed impact of different dark matter models, et cetera. Okay, so yeah, we're hoping to get there soon. I think this is going to be, there's a lot of stuff happening in this field, so I think it's going to be really exciting. Okay, so stellar streams. We expect that the Milky Way is full of these dark matter halos, and the detritus that the galaxies in those halos and the globular clusters in those galaxies left behind as they got accreted onto the Milky Way. And we actually now have, this is kind of amazing, we actually now have about 100 streams that have recently been detected. This was pretty fast in the last 5 years, so a lot of those are globular cluster streams. Some of them are streams from dwarf galaxies. And as I mentioned, we're expecting more soon. So this is really interesting because those streams can probe different things in the halo. Just the counts and the radial distribution of the streams are actually really interesting and actually can tell you more about what came into the halo. But the other thing is that these things can be probes of dark substructures. So you can imagine that you have a stream coming and now you have a dark matter halo and it goes through it. That's what's shown in this simulation, and it should perturb the stream. I think this is really promising, but again, it's also really hard. It's hard observationally and it's hard theoretically. So why is it hard observationally? So this is an example. If you, as I said, I really want to get to these very small halos. If you have a 10 to the 9 solar mass perturber, it can make something very big. If you have a 10 to the 7 solar mass perturber, it makes a little mess, and if you have a 10 to the 6, it's an even smaller mess. And if you then put some observational errors on it, if you have a 10 to the 6 solar mass perturber with typical velocity errors, like 1 kilometer per second is pretty good for most spectrographs, you really can't see it. So we think what you need is to get 100 meter per second radial velocity precision, and that's what we set out to do. Okay, so in order to get this, there's not really any instrument that exists right now that can give you 100 meter per second radial velocity precision for most of the sky, which is what you want, and in a highly multiplexed way. So we're building doing a new survey with 2 new instruments. It's going to be 2 because we want to do all sky. And these are going on the Magellan and MMT telescopes. They'll be basically twin instruments. And we plan to do a 5-year survey and get at least 2 million stellar spectra. So the key idea here is to have enough fibers, so 600 fibers, and enough radial velocity precision. So in order to do that at high efficiency, we actually have a relatively narrow wavelength range, just from about 500 to 600 nanometers. But that's pretty good. You can get the magnesium triplet, which gives you a good measurement for a precise radial velocity. And we also have the sodium doublet. So this is actually going to be a fantastic survey for also mapping the gas in the halo. And in addition to the main thing here, we'll have some other fibers on the focal plane, which are sort of low resolution spectroscopy over a wide wavelength range that are going to be able to go much deeper. And this will be really, really great for fast transient follow-up. If we're already on the telescope, we should be able to get to a new transient in about 2 minutes. And so that could be very exciting for some of the most interesting objects from LSST. This is a small collaboration, and we are going fast. It's really exciting. We're hoping to be on Sky by 2027. So Charlie Conroy and Banaka have been spearheading this. Dan Fabrikant is leading the instrument, and we're having a lot of fun. So back to the streams, right? If you look at 1 kilometer per second, this is an estimate of what halos you would be able to see. You can just see kind of a handful in this above 10 to the 8. If you can get down to this 100 meter per second, you actually should be able to detect a significant population of these perturbers below 10 to the 7. And so we hope that actually gets us into the regime that we have truly dark halos. So this is a simulation here of a stream population, sort of with the streams that we already know and a representative population of perturbers, and just sort of showing you where you can detect different kinds of perturbations. Of course, exactly what that perturbation looks like, is a function of the orbit and other things, and where the stream is, et cetera. So we plan to target about 20 streams. And there's roughly one really clear impact per stream, but you actually should have the impact of something maybe more like 50 per stream if you can do the statistics right. So VIA actually has 4 key goals. The streams is one. I told you briefly about the transients and the gas, and then the other one is to get spectroscopy of the Milky Way satellites. And we actually hope to be able to basically do this for all of the Milky Way satellites, even though it's been a heroic effort from kind of all available telescopes to get spectroscopy of the ultra-faint dwarfs. It's pretty hard because you're often doing it one star at a time. So an example is looking at 20 hours on DMOS for some of these things. So the great thing about VIA is we should be able to, in one pointing, actually get a large number of the stars in most ultrafaints. So we plan to do that essentially for every system that exists. And then for some of the very nearby ones, we'll spend about 10 hours per dwarf. And then we can get down to G of 23 and actually really measure those nearby small things as well as we can. So this is great. We'll get velocity dispersions with better precision than is really possible with most of what has been done, which is really important for the faint end where the velocity dispersions of these things are just a few kilometers per second. And you actually want to distinguish between globular clusters and dwarf galaxies in that regime. So this will really help with that. Measuring metallicities will also really help us. Okay, so I told you about these 3 new probes and the data that is coming that will enable it. In order to really make the most of these data, we do need a lot of new modeling. So we really want to understand the cosmological context of the Milky Way or of our lenses. For all of these methods, we actually need better predictions of small scale of the dark matter and stellar structure all the way into the inner regions of the halo, where most of the current literature is not doing this accurately enough. We need to understand what baryons do to the dark matter halos and the galaxies, and we need ideally to be able to make really nice predictions for the stellar halos and the streams. So I spent a lot of time doing simulations for very large surveys, and I'm kind of thinking about this effort in a similar way. I think we really need a sort of fast and flexible simulation pipeline so that we can really do large statistical samples of Milky Way-like objects in a cosmological context. And we really want our theory predictions not to be the limiting factor in these things. So as I said, I think about this in a similar way to how I've thought about galaxy formation in a cosmological context. We definitely need hydrosimulations to test many things, but we're nowhere near having hydrosimulations that get us to the resolution and the statistics that we are going to need to do this inference. So we kind of want to be somewhere in between where we can use dark matter only simulations that we modify in ways that make sense, learning from hydrosimulations to be able to make those kinds of predictions. So we need to have lots of realizations, vary our galaxy formation models, vary our dark matter models, and really have a fast, flexible approach. And I think this is not a small effort. The data is now good enough that we need to be doing this better than we have. So there's a lot of words on this slide, but this is just to give you a flavor of some of the work my team has been doing in this area recently. So first, making statistical samples of Milky Way mass halos and halos that look a lot like our own Milky Way. So turns out in the Milky Way in particular, we have this, either fortunate or unfortunate situation with a recent major merger, or not major, but medium-sized merger with the LMC. And the LMC actually really impacts our predictions in the Milky Way, so we need to account for that. We need to understand what the disk does to substructure. We really need better substructure tracking. We need, higher resolution simulations that include all of those other things, and we need to test these things with full physics hydro. And then once we have those simulations, we actually need to go closer to the data, right? So thinking about how do we actually make predictions for the stars, How is that dependent on the galaxy formation model? What happens to the globular clusters? So and then how do we actually get into the, make mock catalogs for surveys? So we're thinking hard about this pipeline. This is something we've been working on. I'll just give you a few highlights of this. So the LMC, the Milky Way disk, and subhalo tracking all really impact the predictions at a level that matter for our current constraints. So the fact that we have a recent accretion of the LMC actually leads to 80% more satellites in the inner region of the halo than you would have if you didn't have that merger. So you want to be able to make sure you account for that and then also connect that to your broader cosmological predictions. You'd like to understand what the Milky Way itself does to destroying the satellites that might interact with it. That turns out to be an important factor. It can reduce the number of substructure by roughly a factor of 2, at least in the inner regions of the halo. And so you want to be thinking about, full self-consistent growth of the Milky Way. It actually matters a lot what the Milky Way, what its mass was at redshift 1 for what happens to the subhalo. So we've done a recent study that has self-consistent disk growth in a dark matter only simulation with these kind of statistics. And then the last thing I'll mention here is that most modern halo finders aren't really that good, including the ones that I've written. So Rockstar is an example of a halo finder that is wide use that we put together some time ago. And a typical subhalo that comes in Rockstar, independent of the resolution of the simulation, gets lost after a few orbits. So that's a problem. And Rockstar is better than most. And this is not just a problem in dark matter only simulations. It's also a problem in hydro, where actually sometimes the problems are much worse than you think they are. So we have there's a few things out there. This is a really a recent study from Phil Mansfield, where we really actually track the particles themselves, and we're actually able to typically track things for more like 10 or more orbits rather than just a few. So that also makes a pretty big difference. Using the same ideas here of tracking dark matter particles, we've developed a new approach to star tracking in these simulations. And what I like about this is that it's actually quite flexible. So you can kind of choose your galaxy halo connection. You can choose the size of your galaxy, your metallicity, those kinds of things, and you can paint your stars in that way. And that enables you to make predictions for what happens to the star particles. One thing that we've been working on recently, so most dark matter, so most satellite galaxies that get accreted into the Milky Way have been there for a while and probably have already started to be tidally disrupted. And typically what's done now is we talk about satellites and we talk about streams, but we don't talk about anything in between. So I think in order to really make the most of the data, we want to be able to talk about the whole continuum from a galaxy to a dwarf galaxy stream. And these measurements that I told you about actually are going to be able to measure the tidal features around the dwarf galaxies. So we'd like to be able to predict them. And so this is something we're working on now. Okay, so I know I'm also almost out of time. So just to say that we've got some really nice methods to probe small scale structure. We have really beautiful data coming very soon from imaging of half the sky to large area space-based imaging to high resolution spectroscopy. We have a lot of work to do to enable our models and our statistical inference to keep up with these incredible data. So I will end there, and I will just say that, I think if you remember one thing, I think, remember that I think these surveys will have sensitivity to detect dark halos below the limit of galaxy formation this decade. So we should do the work that we need to do to make that happen. Thanks.